Welcome to For Science Salah Lotfy channel, where science meets curiosity. في هذه القناة لا نكتفي بعرض الأبحاث العلمية، بل نترجمها إلى المعرفة التي تصل إليك أينما كنت. Our mission is to make global scientific research understandable, accessible, and multilingual. جميع الفيديوهات العلمية هنا مترجمة إلى اللغة العربية، بالإضافة إلى لغات عالمية أخرى. French, Spanish, German, Urdu, and more. Because science speaks every language. نعم، العلم يتحدث بكل اللغات، ونحن نحرص أن يصلك بلغتك. If you're passionate about science, you're in the right place. اشترك الآن وابدأ رحلتك مع العلم خطوة بخطوة. For Science Salah Lotfy channel, العلم للجميع.
Welcome to For Science Salah Lotfy channel. This channel is always drawn to groundbreaking scientific discoveries, the kind of knowledge that reshapes our understanding of the universe. One such moment came recently, when Professor Dr. Ibrahim Abdel-Gawad, Professor of Chemical Engineering in the Production Sector, and General Coordinator of the Modeling and Simulation Group at the Nuclear Materials Authority, shared a remarkable piece of news in a specialized scientific group. It was morning, before even sipping my first cup of coffee, when I came across his post. And it was not just news, it was a scientific achievement worth pausing at. In the fast-paced world of scientific discovery, a breakthrough can begin, not in a lab, but with a single, electrifying post. That's what happened when Professor Ibrahim Abdel-Gawad shared a fascinating accomplishment. The message was simple, yet its implications were so profound it quickly captured the attention of physicists and tech enthusiasts worldwide, sparking a wave of curiosity. The post declared, "On the atomic scale, scientists have developed the world's smallest measuring tape." This wasn't a physical tape, of course, it was a mathematical framework so precise it could pinpoint individual atoms with an accuracy that was previously science fiction. Imagine trying to measure a single grain of sand on a vast windswept beach. Now, shrink that grain down a billion times to the size of an atom, where quantum uncertainty reigns, and you begin to grasp the monumental challenge these scientists had overcome. This was far more than an intriguing metaphor. At the University of Vermont, a team had achieved a landmark in quantum measurement, determining the position of atoms on a crystal surface with unprecedented precision. Why is this so revolutionary? The ability to know exactly where atoms are is the first step toward controlling them. This opens the door to engineering materials from the ground up, creating substances with incredible new properties. It could revolutionize quantum computing, where atomic positions are key for storing data, and accelerate the development of hyper-efficient solar cells and next-generation medical sensors. The groundbreaking work was led by Professor Clougherty and his student, Nam Dinh. Their approach was as elegant as it was unconventional. They reached back in time over a century to a classical model developed in 1900 by the renowned British physicist Sir Horace Lamb. Lamb was a master of classical mechanics, famous for his work on how waves and vibrations move through traditional materials, long before the quantum world was fully understood. Lamb's model, however, was from a pre-quantum era. It couldn't account for the strange, probabilistic rules governing the subatomic realm. This is where the genius of Clougherty and Dinh came in. They took Lamb's classical framework and meticulously reformulated it, weaving in the complex principles of quantum mechanics. Using advanced mathematical tools, they transformed a century-old idea into a cutting-edge technique, allowing them to describe the subtle vibrations of atoms at the quantum level with unmatched accuracy. It was a beautiful synthesis of old and new, a testament to how classical intuition can illuminate the mysteries of quantum precision. In our everyday world, the rhythm of life is often a story of fading echoes. When you pluck a guitar string, its vibrant note doesn't last forever. When you set a swing in motion, its soaring arc inevitably shrinks. These are classic examples of what physicists call damped harmonic oscillators. They are systems that naturally want to oscillate back and forth, but they constantly lose energy to their surroundings through forces like friction and air resistance. The beauty of this classical world is its predictability. We can calculate precisely where that swing will be and how fast it's moving at any given moment. But what happens when we leave our familiar large-scale world behind and plunge into the bizarre realm of the ultra-small? At the atomic scale, the rules of the quantum world take over. Here, atoms within a crystal lattice or molecules in the air also vibrate, but their dance is governed by a completely different and far stranger set of principles. Describing these quantum vibrations becomes extremely tricky. The core of the problem lies with one of quantum mechanics' most famous pillars, the Heisenberg uncertainty principle. It tells us you cannot precisely know both the position and velocity of a particle at the same time. Imagine trying to measure an atom's position. The very act of measurement, perhaps by bouncing a particle of light off it, inevitably gives it a kick, changing its velocity in an unpredictable way. This isn't a flaw in our instruments, it's a fundamental feature of reality known as quantum backaction. Observing a quantum system is never a passive act. Your measurement introduces a new layer of uncertainty. For nearly 90 years, since the birth of quantum theory itself, physicists tried to solve the riddle of the damped quantum oscillator, without success. The greatest minds of the 20th century developed powerful tools to describe idealized, closed quantum systems that don't lose energy. But the real world is messy. The problem was clear. How do you create a model that accounts for continuous energy loss, while also respecting the jarring, uncertain kicks from quantum backaction? The more precisely you measure an atom's position, the less certain you become about its speed, and vice versa. This paradox left a gaping hole in our understanding, a puzzle that stumped generations of scientists. To overcome this, the Vermont team employed an advanced mathematical tool known as the multi-mode Bogoliubov transformation. This allowed them to untangle the complex interactions of an atom with its neighbors, leading to a new quantum state they called the multi-mode squeezed vacuum. This special state reduces quantum noise in the atom's position at the cost of increasing uncertainty in its velocity, and this trade-off was exactly what made ultra-precise measurements possible. Think of it this way. Imagine a tiny beam of light in a dark room. If you try to pinpoint its exact location, you lose track of its movement. If you try to track its movement, you can't locate it precisely. What the researchers did was like placing a special lens over that light, reducing the blur in its position. Suddenly, the exact location becomes crystal clear. As Professor Clougherty himself explained, by reducing the uncertainty in an atom's position, we can measure it with a precision never before possible. The implications of this newfound control are profound. This breakthrough paves the way for quantum-scale measuring devices, the smallest, most precise rulers in existence. Imagine trying to build the next generation of computer chips where components are just a few atoms wide. With these quantum rulers, we can move beyond estimation and achieve true atomic-level quality control. We could design and verify structures atom by atom, ensuring perfect alignment and function. This isn't just about measuring for the sake of it, it's about providing the blueprint and the tools for the next revolution in nanotechnology and materials science, building stronger, lighter, and more efficient materials from the ground up. This precision also leads to the creation of ultra-sensitive sensors. In medicine, this could mean diagnostics that are non-invasive and incredibly early. Imagine a sensor capable of detecting the faint, telltale magnetic fields produced by the human brain, allowing for earlier and more accurate diagnosis of neurological disorders like Alzheimer's or epilepsy, or a device that could spot the signature of a single rogue cell in a blood sample, catching cancer at its absolute earliest stage. In space exploration, these sensors could map the gravitational fields of distant planets with such fidelity, they could detect underground oceans on icy moons or hidden cave systems on Mars, all from orbit, guiding our search for extraterrestrial resources and even life. The research also promises next-generation atomic clocks and navigation systems. Today's atomic clocks are already marvels, using the consistent vibration of atoms as a near-perfect pendulum. But by better understanding and controlling quantum noise, we can build clocks that are orders of magnitude more accurate. This leap in precision has a direct impact on technologies like GPS. More accurate clocks in orbit mean more accurate positioning on the ground, not just getting you to the right street, but enabling fully autonomous vehicles that require centimeter-level precision to navigate our world safely and efficiently. And it even connects directly to one of the greatest discoveries of our time, the first detection of gravitational waves, which won the Nobel Prize in 2017. The LIGO observatories are essentially the most sensitive rulers ever built, designed to detect a distortion in space-time smaller than the width of a proton. To achieve this, they had to overcome the fundamental limit of quantum noise. The solution? Injecting squeezed states of light into the detectors, a direct application of the physics we've been exploring. This technique quiets the quantum fuzziness, allowing the faint whisper of a gravitational wave to be heard. It's a stunning testament to how fundamental quantum theory enables monumental discoveries about our universe. In other words, this is not just about atoms vibrating in theory, It's about building the tools that could reshape technology across countless fields, from the nanoscale to the cosmic scale. We are moving from being passive observers of the quantum realm to becoming active architects, engineering its properties to build a new future. When we look out into the cosmos, we see a universe of profound order. In the heart of every star and every nebula, every atom vibrates, not in random chaos, but like a note in a cosmic symphony, following precise and elegant laws. This inherent mathematical structure is what makes the universe knowable. It's a principle that echoes through spiritual traditions. As the Quran reminds us, indeed, we have created everything according to a measure. This scientific quest to understand and harness the measure of an atom can be seen as uncovering another layer of that intricate, preordained design, a convergence of inquiry and awe. To achieve this, scientists needed a new language. In the reformulated quantum model of Willis-Lamb, the vacuum of space is not empty, but a sea of fluctuating fields. Then, through a powerful mathematical tool called the Bogoliubov transformation, these complex vibrations become solvable equations. This transformation acts like a special lens, allowing physicists to redefine the system and turn the chaotic noise of the quantum vacuum into predictable, squeezed states. By squeezing the uncertainty in one property, we gain unprecedented certainty in another. And so, measurement itself becomes an act that shapes reality, allowing us to coax the universe into revealing its secrets with a clarity nature would not normally permit. For those interested in the technical side, the Bogoliubov transformation redefines creation and annihilation operators. New annihilation operator, BK equals sign UKAC plus VKAK plus, new creation operator, BK plus equals sign UKAC plus VKAK with the quantization condition, UK2, VK2 equals sign 1. This diagonalizes the Hamiltonian, making it easier to analyze the ground state and energy spectrum of the system. This elegant mathematical tool is what allowed researchers to reduce quantum uncertainty in one dimension, pushing the limits of what we can measure. At 4 Science Salah Lotfy channel, we are inspired not only by the science itself, but also by the way such discoveries remind us of the profound order embedded in creation. Thanks to Professor Dr. Ibrahim Abdel-Gawad for drawing our attention to this scientific milestone, and to the team at the University of Vermont for pushing the boundaries of human knowledge. Stay tuned as we continue to bring you more stories where science meets inspiration. Welcome to For Science Salah Lotfy channel. In today's episode, we explore a recent and remarkable contribution to quantum physics. The research we are discussing is titled Quantum Lamb Model. It was conducted by Professor Dennis Clougherty and physics PhD student Nam Dinh from the Department of Physics at the University of Vermont, Burlington, USA. Their work was published in the prestigious journal Physical Review Research, Volume 7, LO3 2004, in the year 2025. The paper was received on March 27, 2025, accepted on June 17, and officially published on July 7, 2025. The research revisits a classic model from over a century ago. In 1900, British physicist Horace Lamb studied how a vibrating particle embedded in an elastic medium gradually loses energy due to the waves it generates, a phenomenon known as damping. But this was before the era of quantum mechanics. For decades, scientists struggled with a key challenge. How can this system be described in the quantum world, where Heisenberg's uncertainty principle rules and makes simultaneous measurement of position and velocity impossible? In this new study, Clougherty and Dinh presented a quantum version of the Lamb model. What makes their work remarkable is that they found an exact solution, something physicists had been chasing for more than 90 years. By applying a powerful mathematical method known as the multi-mode Bogoliubov transformation, they managed to diagonalize the Hamiltonian of the system and reveal its fundamental behavior. Their analysis showed that the true ground state of the system is a multi-mode squeezed vacuum state. This is a very special quantum state where the uncertainty in the particle's position is reduced, at the cost of increasing the uncertainty in its velocity. Such states are not only of theoretical interest, they are also the backbone of today's most advanced precision measurement technologies, including the detectors that first observed gravitational waves. The significance of this discovery is profound. It provides an exactly solvable model of a damped quantum harmonic oscillator, a deeper understanding of how quantum systems dissipate energy, and a foundation for designing ultra-precise quantum sensors, atomic clocks, navigation systems, and quantum devices that may one day revolutionize medicine, electronics, and space exploration. The quantum Lamb model stands as both a tribute to classical physics and a triumph of modern quantum theory. Through the work of Professor Dennis Clougherty and Nam Dinh, published in Physical Review Research in 2025, a century-old puzzle has finally been solved, opening new horizons in the world of quantum science. Stay with For Science Salah Lotfy channel as we continue to bring you closer to the frontiers of discovery. Everything you see, everything you can touch is in a state of constant, unseen motion. The atoms that make up the chair you're sitting on, the screen you're looking at, the air you breathe are not still. They're vibrating, jiggling, dancing to a silent rhythm dictated by the fundamental laws of physics. This ceaseless vibration is what we measure as temperature. The hotter something is, the more vigorously its constituent particles are shaking. It's an idea that goes right to the heart of what matter is: a universe of perpetual motion, hidden just beneath the surface of our everyday experience, a cosmic ballet playing out on a scale too small for our eyes to witness directly. This concept of vibrating particles isn't new. Physicists have been grappling with it for a very long time. Over a century ago, back in the year 1900, Horace Lamb developed a model to describe this phenomenon. He imagined a single particle, an oscillator, embedded within a larger material. Lamb wanted to understand what happens when this particle starts to vibrate. His classical model was a masterpiece of Victorian physics. It predicted how the particle's energy would dissipate, how its motion would fade into the surrounding medium. Lamb's work laid a foundational stone for our understanding of how energy moves through materials. Think of it like a single bell ringing in a vast cathedral. The sound doesn't just stay at the bell, it travels outwards, its energy spreading through the air, reflecting off stone walls, eventually diminishing until silence is restored. Lamb's model was the mathematical equivalent for a single vibrating atom. It provided a classical, deterministic way to think about how a localized disturbance loses energy to its environment: damping. It was a beautiful and elegant piece of physics for its time. Think of it another way. Imagine you are standing on a trampoline holding a heavy ball. If you start bouncing the ball up and down, you will send vibrations through the trampoline surface. These vibrations, spreading outwards, are carrying energy away from you and the ball. You would find it increasingly difficult to keep the ball bouncing with the same height, because the trampoline is effectively resisting your motion by turning it into waves. The particle in a material feels a similar effect. Its own movement creates a back reaction from its environment, a resistive force that dampens its oscillation over time. It's a universal principle of action and reaction. This process of damping is absolutely everywhere in our universe. It is why a plucked guitar string eventually falls silent, its vibrations transformed into the sound waves we hear. It's why a bouncing ball eventually comes to rest, its energy converted into heat and sound with each impact. Without damping, every vibration would continue forever, and the universe would be a cacophony of unending noise. Imagine dropping a pebble into a perfectly still pond. The pebble's impact creates a disturbance, a vibration that doesn't stay in one place. It propagates outwards as a series of concentric ripples or waves. These waves carry energy away from the point of impact. As the energy spreads out across the surface of the pond, the initial disturbance at the center becomes smaller and smaller until it vanishes completely. The energy hasn't disappeared, it has simply been distributed throughout the water. This is the essence of damping. This same principle applies to a vibrating particle within a material. When the particle jiggles back and forth, it pushes and pulls on its neighbors. This push and pull creates a chain reaction, a wave of motion that travels out through the material, much like the ripples in the pond or sound waves traveling through the air. Each wave that radiates away from the particle carries with it a tiny packet of the particle's vibrational energy. This constant leakage of energy is a form of friction. The very act of creating waves in its surroundings slows the particle down, causing its vibration to gradually weaken and ultimately stop. But the universe is far stranger and more wonderful than classical physics imagined. Lamb's model worked for the macroscopic world, but it couldn't capture rules of the microscopic realm. Individual atoms and subatomic particles obey quantum mechanics. As technology lets us build on that scale, we need a quantum version of Lamb's idea to guide us. So, how does a vibrating particle actually lose its energy? The process is both intuitive and deeply profound. Each wave that radiates away from the particle carries with it a tiny packet of the particle's vibrational energy. This constant leakage of energy is a form of friction. The very act of creating waves in its surroundings slows the particle down, causing its vibration to gradually weaken and ultimately stop. It's a universal principle of action and reaction. The world of the 21st century is built on technologies that Horace Lamb could have only dreamed of. We are engineering materials at the atomic level. We are building quantum computers that promise to solve problems impossible for any classical machine. We are creating sensors of astonishing precision. In these new frontiers, we are no longer dealing with large collections of atoms behaving in a predictable, classical way. Instead, we're manipulating individual quantum systems, where the peculiar and counterintuitive rules of quantum mechanics reign supreme. This is precisely why scientists needed to revisit Lamb's century-old model and build a new version from the ground up. In the realm of quantum computing, for instance, information is stored in qubits. Qubits can be tiny superconducting circuits. Qubits can be individual trapped ions. These qubits are, in essence, microscopic oscillators. The enemy of a quantum computer is a phenomenon called decoherence, which is really just a quantum form of damping. Unwanted vibrations can cause the qubit to lose its delicate quantum state. Interactions with the surrounding environment can also destroy the information it holds. To build better, more stable quantum computers, we desperately need to understand exactly how this quantum damping works. We need to find clever ways to protect our qubits from it. Similarly, our quest for ever more precise measurements depends on controlling quantum vibrations. Consider the incredible LIGO experiment, which detects the faint ripples in spacetime known as gravitational waves. The detectors are so sensitive that they can measure a distortion smaller than the width of a proton. At this level of sensitivity, even the tiniest quantum vibrations in the detector's mirrors can create noise that masks the real signal. Understanding how these quantum-level oscillations are damped and how their energy dissipates is therefore not just an academic exercise. It is fundamental to our ability to peer deeper into the cosmos and unlock its greatest secrets. So, the motivation was clear. We needed a model that could take Lamb's beautiful classical idea, an oscillator losing energy to its environment, and recast it in the full, strange language of quantum theory. We needed a model that could handle not just simple vibrations, but the ghostly probabilities and inherent uncertainties that lie at the very heart of reality. To build their quantum model, physicists returned to a beautifully simple picture, one that Lamb himself would have recognized. Imagine a single tiny bead. This bead is our quantum particle. It's attached to a fixed point by a tiny, perfect spring. If you pull the bead and let it go, it will bounce back and forth rhythmically. This is a quantum harmonic oscillator, one of the most fundamental building blocks in all of quantum mechanics. It's the quantum equivalent of a pendulum swinging or a weight bobbing on a spring, a system that wants to oscillate at a specific natural frequency. Now, to introduce the concept of damping, the process of slowing down, we need to connect this oscillator to its environment. So let's attach our bead on a spring to a very, very long string that stretches out to infinity. When our bead vibrates, it doesn't just bounce in isolation. Its motion sends tiny waves traveling down the length of the string, carrying energy away from the bead forever. This setup, a single oscillator coupled to an infinite line, is the perfect physical analogy for the quantum problem. The bead is the quantum system we care about, and the infinitely long string represents the vast environment into which its energy can dissipate. This is where the magic of quantum mathematics comes in. While the physical picture is simple, describing it requires some powerful tools. Instead of predicting the exact position of the bead, quantum mechanics describes it with a wave function, a cloud of probability. The lowest possible energy state of our bead isn't perfectly still. It's called the ground state, a state of minimum unavoidable quantum jiggling. To solve what happens when the bead vibrates, welcome to For Science Salah Lotfy channel. Today, we continue our journey into the heart of quantum physics, exploring one of the most elegant and exact solutions to a problem that has puzzled scientists for over a century: the quantum Lamb model. Imagine a tiny bead of mass m attached to a spring and connected to a long string under tension. As the bead vibrates up and down, it creates acoustic waves along the string. These waves carry energy away, gradually damping the bead's motion. This is the essence of the classical Lamb model proposed in 1900. But in the quantum world where uncertainty rules, things become far more complex. To truly understand and predict the behavior of our quantum bead, a qualitative description isn't enough. We need to move from concept to calculation. To achieve this, physicists introduced a set of crucial mathematical tools, parameters that precisely describe how strongly the bead interacts with each part of the string. Think of these as the dials and knobs of our model, allowing us to tune the strength of the connection between our quantum system and its environment. Without them, we can't answer the most important questions like how quickly the bead will lose its energy. These are known as coupling parameters, represented by the Greek letter gamma with a subscript n or gn. The term coupling is key. It signifies the bridge through which energy flows from the bead to the string. But why the subscript n? This is because the string has a whole family of possible vibrational patterns, or modes. The n in gn tells us that there's a separate coupling strength for each and every one of these modes. Some modes might couple strongly, readily accepting energy, while others might be weakly coupled. Remarkably, these abstract parameters can be expressed directly in terms of the tangible physical properties of the model. For instance, the string's tension plays a critical role. A higher tension makes the string stiffer, changing how it responds to the bead's oscillations. Then there's the mass density. A denser, heavier string has more inertia, making it harder for the bead to set it in motion, thus affecting the rate of energy transfer. Finally, the speed of sound in the medium dictates how quickly the vibrational energy propagates away from the bead. A faster speed means energy is whisked away more efficiently. Now, here's where the model takes a giant leap towards realism. A real-world environment has a virtually infinite number of ways to absorb energy. To mimic this, physicists consider what happens as the number of string modes, n, approaches infinity. This is the thermodynamic limit. In this limit, the discrete vibrational modes of the string blur together, forming a continuous spectrum. The string transforms from a simple object into a perfect energy sink, an environment that can absorb any energy the bead gives it without ever sending it back. And this is the ultimate payoff. In this limit, the bead can radiate its vibrational energy continuously into the environment. Instead of losing energy in jerky packets, its energy drains away in a smooth, uninterrupted flow. This allows researchers to precisely study quantum decay, calculating the bead's half-life and mapping its energy decay curve. This simple model, pushed to its limit, becomes a powerful analog for understanding how a quantum system gives up its energy to the world around it. The system is described mathematically by a Hamiltonian. This Hamiltonian includes the bead's vibration, the vibrational modes of the string, and the interaction between them. To solve it, scientists use the multi-mode Bogoliubov transformation, a powerful mathematical tool that diagonalizes the Hamiltonian and makes the system solvable. This transformation preserves the fundamental bosonic commutation rules and requires constructing large symplectic matrices that encode the coefficients of the transformation. The result is profound. The ground state of this quantum system is always a multi-mode squeezed vacuum state. In this state, the uncertainty in the bead's position is reduced, while the uncertainty in its momentum increases. This is not just a theoretical curiosity. It connects directly to real-world technologies. Squeezed states are the backbone of precision measurements, including the detection of gravitational waves. As damping increases, the position uncertainty becomes smaller, perfectly consistent with earlier findings by Caldera and Leggett. The study then moves deeper, analyzing the vibrational decay of the bead. By displacing the bead slightly and letting it evolve, researchers calculated the bead's position over time. The decay rate of this vibration emerges naturally from the model. For weak coupling, the decay rate matches both classical predictions and results from Fermi's golden rule, a cornerstone of quantum mechanics. But there's more. The decay of the vibrating bead is accompanied by the emission of new quantum excitations called Bogoliubons. The probability of emitting a single Bogoliubon of a given frequency can be calculated directly from the Bogoliubov coefficients. In fact, the spectrum shows that about 90% of the emission is carried by single Bogoliubons, with a nearly symmetric distribution around a slightly red-shifted peak. This provides an exact quantum picture of how energy is radiated away from the bead into its environment. Within any physical model, there are rules and boundaries. The quantum Lamb model is no different. While we can mathematically explore a vast landscape of possibilities by adjusting its parameters, things like the mass of our quantum bead or the stiffness of our spring, not every combination corresponds to a reality we can observe. The model itself predicts a fundamental limit, a critical coupling strength that acts as a hard boundary between the possible and the impossible. To understand why, we need to look at the system's Hamiltonian. In quantum mechanics, the Hamiltonian is a mathematical operator that represents the total energy of the system, its kinetic energy, plus its potential energy. For a system to be physically stable, its energy must have a floor, a lowest possible value known as the ground state. If the interaction strength or coupling is pushed beyond this critical threshold, the Hamiltonian mathematically breaks down. It no longer has a well-defined minimum. This would imply the system could spiral down to infinitely negative energy, a scenario that is physically nonsensical. It's like a ball rolling down a hill that has no bottom. Therefore, if the interaction becomes too strong, the Hamiltonian loses stability, meaning the system as described simply cannot exist in our universe. Fortunately, this theoretical instability rarely poses a problem in the real-world systems the model describes. Consider the physical forces at play in a quantum system, like an atom interacting with a light field. The strength of this interaction has its own natural limits, so under realistic conditions, long before the theoretical coupling becomes strong enough to break the model, other physical constraints come into play. It's analogous to stretching a real spring. You can only stretch it so far before the material itself physically breaks. The model's stability boundary is often far beyond this physical breaking point, ensuring that for all practical purposes, the system remains stable and well-behaved. But this boundary isn't just a mathematical curiosity, it's a source of profound insight. This delicate balance between stability and instability is part of what makes the quantum Lamb model so powerful. By understanding precisely where this line is drawn, we gain a deeper appreciation for the fundamental rules governing the quantum world. It allows us to predict the limits of physical systems and even design new ones that operate close to this edge, where sensitivity is maximized. This is crucial for developing next-generation quantum technologies. The model's true strength lies in its dual nature. It elegantly captures both the familiar classical physics of damping, the gradual loss of energy you see in any real-world oscillator, and simultaneously incorporates the uniquely quantum mechanical limits of stability, providing a complete and predictive picture. The implications of this exact solution are wide-reaching. It offers a model for understanding nano-electromechanical systems, where vibrations interact with electronic devices, quantum acousto-dynamics, where mechanical resonators couple to each other, quantum optics and cavity systems, where vibrons may interact with photons, and potentially even magnetic materials, where vibrons couple with magnons. In all these areas, the quantum Lamb model provides a clear, exact framework to describe energy dissipation, quantum squeezing, and the flow of information at the smallest scales. Our journey through the intricate world of quantum dissipation has brought us to a remarkable destination. We've explored how even the most fundamental objects in the universe interact with their environment, a process that is not a flaw, but a feature of reality itself. As we conclude, let's weave together the threads of our discussion to appreciate the full tapestry of the quantum Lamb model. To summarize, our story begins by reaching back in time. The quantum Lamb model extends a classical idea, first conceived by the mathematician Horace Lamb in 1900, into the strange and wonderful quantum regime. Lamb's original model was a brilliant piece of classical physics, describing how a simple vibrating object would lose energy to a surrounding medium. For over a century, it remained a cornerstone of classical theory, but a direct and complete quantum version remained elusive. This new work finally builds that bridge, taking a century-old concept and fully equipping it for the quantum age. The mathematical heart of this breakthrough is the multi-mode Bogoliubov transformation. It provides an exact solution, a rare and precious thing in quantum physics. Imagine a complex web of interconnected springs, where pushing one sends chaotic ripples through the entire system. The Bogoliubov transformation is like a mathematical lens that allows us to see this chaos not as a web, but as a set of simple, independent vibrations. It finds the true fundamental modes of the system, simplifying an impossibly complex problem into one we can solve perfectly. This exact solution reveals a profound insight. The system's true ground state, its state of lowest energy, is a squeezed vacuum state. In quantum mechanics, a vacuum isn't empty. It's a sea of fluctuating energy and virtual particles, governed by the Heisenberg uncertainty principle. This model shows that as the damping, the interaction with the environment, increases, the vacuum state becomes squeezed. This means the inherent quantum uncertainty in the oscillator's position is reduced, effectively pinning it down more precisely. This comes at a cost, of course, as the uncertainty in its momentum increases. but it demonstrates a powerful way that the environment can fundamentally alter the quantum nature of an object. Crucially, the model delivers explicit formulas for the decay rate, and these formulas are fully consistent with both classical physics and quantum theory. This is a critical test for any new quantum model. It demonstrates the correspondence principle in action, the idea that a new, more general theory must reproduce the results of the old established theory in the appropriate limit. The quantum LAM model doesn't just work in the quantum world. It gracefully connects back to the classical predictions made over 100 years ago, validating its own foundations. And it predicts the emission spectrum of new quantum excitations, which we call Bogoliubov bonds, that carry away the vibrational energy. These are not fundamental particles like electrons, but quasi-particles, collective excitations of the entire system. Think of them as the quantized packets of energy that arise from the interaction between the oscillator and the field. The model predicts the exact spectrum of these emissions, providing a unique fingerprint of the dissipation process that could, in principle, be measured in an experiment. This work not only solves a century-old puzzle in theoretical physics, but also opens doors to the next generation of quantum technologies. The fight against decoherence, the loss of quantum information to the environment, is the central challenge in building functional quantum computers. Models like this give us the theoretical tools to understand, predict, and potentially control that process. The principles of squeezing and environmental interaction are also vital for developing quantum sensors with precision far beyond what classical devices can achieve. Here at For Science Salah Lotfy channel, we are inspired by how theory, mathematics, and experiment come together in moments like this. It's a testament to the power of human curiosity and the relentless pursuit of knowledge. A single, elegant mathematical framework can illuminate a process that happens everywhere, from the quantum foam to the vastness of space, helping us to reveal the hidden structure of reality. The story of science is a continuous thread, connecting generations of thinkers. A question posed in the age of steam engines can find its answer in the era of quantum bits. Stay with us as we continue to explore these incredible discoveries that link the physics of the past with the quantum innovations of the future.
I'd like to take a moment to express my deepest gratitude. I am Professor Salah Lotfy from the Egyptian Atomic Energy Authority. On behalf of For Science Salah Lotfy channel, I extend my sincere thanks, appreciation, and respect to the brilliant researchers who made this significant contribution to science, solving a problem that has challenged the physics community for nearly a century. This achievement not only honors the legacy of scientific inquiry, but also opens new doors for the future of quantum research and technology. So, with great admiration, I salute Professor Dennis Clougherty and physics PhD student Nam Dinh from the Department of Physics, University of Vermont, Burlington, USA. Your dedication and insight have advanced human knowledge in profound ways. From Cairo, Egypt, with respect and appreciation, this was For Science Salah Lotfy channel.
Now, we present a special commentary by Professor Dr. Ibrahim Abdel-Gawad, Professor of Chemical Engineering, Production Sector, and General Coordinator of the Modeling and Simulation Group at the Nuclear Materials Authority. Here is his reflection on the research featured in this episode.
The images presented here capture the essence of advanced quantum mechanics in a visual form. The first image demonstrates energy distribution before and after the Bogoliubov transformation. This transformation reshapes the wave function and reorganizes the distribution of energy, highlighting interference and fluctuations in quantum fields. It deepens our understanding of superposition and opens doors to potential applications in quantum computing. The second image portrays a squeezed quantum state. In this case, quantum noise is reduced in one observable, allowing extraordinary precision in measurement, while uncertainty shifts into another variable. This principle is the foundation of future high-sensitivity quantum sensors and quantum encryption technologies. At the heart of this approach lies a powerful philosophical point. This is not a violation of Heisenberg's uncertainty principle. Rather, it is a geometric reinterpretation. By restructuring the measurement framework, we do not break the principle. Instead, we redefine the context in which it operates. This shows us that modern physics does not negate the fundamentals. It re-articulates them through more advanced tools. The analytical results and MATLAB-supported simulations confirm that the Bogoliubov transformation is far more than a mathematical device. It is a reconstruction of the quantum system itself. Energy is no longer seen as static, but as a dynamic entity, shaped by both environment and measurement. Quantum noise is redistributed, not eliminated. Probability waves are reshaped, not broken. The message is profound. The boundaries of measurement are not absolute, but conditional, governed by the geometry of the system we create. Within these squeezed states, quantum noise decreases, and measurement precision surpasses classical limits. This is not just a technical improvement. It is a mathematical art of engineering reality. Here, measurement transforms into a creative act, sculpting probabilities, reshaping observables, and redefining what is possible in the pursuit of knowledge. Ultimately, science and philosophy converge. What we see in these models and transformations is more than equations. It is a glimpse into the profound harmony of creation. Indeed, we have created everything according to a measure. Surah Al-Qamar, verse 49. This verse captures not just a law of physics, but the philosophy of existence itself, that all is balanced, calculated, and measured with divine wisdom. Each discovery is a reflection, each equation a verse, and every measurement a form of contemplation on the order of the universe. This is the beauty of science, a journey of both intellect and spirit.
As we come to the end of this episode, I, Professor Dr. Salah Lotfy, professor at the Egyptian Atomic Energy Authority, would like to extend my heartfelt gratitude to Professor Dr. Ibrahim Abdel-Gawad, Professor of Chemical Engineering, Production Sector, and General Coordinator of the Modeling and Simulation Group at the Nuclear Materials Authority. Your insightful commentary and valuable reflections have truly enriched this scientific discussion and have helped us all appreciate the depth and importance of this remarkable research. And of course, my thanks go to you, our dedicated audience. Your support, attention, and curiosity are what make this journey worthwhile. I invite each of you to share your thoughts, reflections, or even your questions about this research right here in the comments section below this video. Your interaction not only strengthens our community, but also helps us all grow together in the pursuit of knowledge. Stay engaged, stay curious, and let's continue this journey of science and discovery together.